Usually when we think about our dreams or just our sleeping minds in general, they feel like this impenetrable, locked vault.
Oh, absolutely. Total black box.
Right. We go to sleep, the heavy door swings shut, and whatever happens inside that vault is just a private, chaotic mystery. I mean, we might remember a disjointed fragment here or there when we wake up, but the actual real-time process of our sleeping brain reviewing the day, it's completely sealed off from the outside world.
It is. And, historically, science could maybe peek through the keyhole, right? Like they could tell us what general state of sleep you're in based on raw electrical activity.
Like REM sleep or whatever.
Yeah, exactly. But actually opening the door, actually reading the specific meaningful contents of your thoughts while you slept, I mean, that remained firmly in the realm of science fiction. The tools to decode that level of semantic meaning they just did not exist.
But that vault has just been cracked wide open. So welcome to today's deep dive. We're looking at a genuinely groundbreaking 2026 paper. This was published in the journal Neuron by Chen and colleagues.
A phenomenal piece of work.
Truly. And the mission for this deep dive today is to explore something the researchers call the sleep interpreter. It is an artificial intelligence system that can literally decode the semantic content, meaning the actual concept of what you were thinking about from your brainwaves while you were fast asleep.
And the sheer scale and rigor of this research really set a new standard. We are talking about analyzing nearly 1,000 hours of overnight sleep data.
Wow.
Yeah, plus 400 hours of waking data, all meticulously collected from 135 different participants. I mean, it represents just a monumental leap in our ability to interface with the human nervous system.
So by the end of our conversation today, you listening are going to understand exactly how artificial intelligence is building a bridge between our waking and sleeping minds.
It's fascinating.
It is. But to appreciate the solution, we first have to understand the roadblock, right? Why has reading a sleeping mind been so historically impossible? So let's talk about the generalization gap.
Right. So the generalization gap is this massive computational hurdle in neuroscience. Imagine you want to train a computer algorithm to read electrical brain waves, specifically EEG signals.
Right.
You wire someone up and you train this decoder while the person is wide awake. You show them pictures, you play sounds, and you map out exactly what their brain's electrical signature looks like when they think of, say, an apple.
Makes sense.
And the decoder gets incredibly accurate at spotting the quote-unquote apple pattern. But the moment you take that perfectly trained decoder and apply it to their brain activity while they're sleeping, it completely fails.
It just breaks.
Hits a brick wall. Total garbage output.
But why does that happen, though? Conceptually, an apple is still an apple. The brain is still the brain. Why wouldn't the awake pattern match the sleep pattern?
Well, the physiological reality of the sleeping brain is that it speaks an entirely different electrical language.
Oh, interesting.
Yeah, so when you enter non-rapid eye movement sleep, or NREM sleep, and specifically when you drop into the deep N3 stage, your brain begins to generate these massive, slow, highly synchronized electrical sweeps.
Like big waves?
Exactly. They're literally called slow oscillations, or SOs. These are huge amplitude, incredibly low-frequency waves that completely dominate the entire EEG recording.
Okay, let's unpack this for you listening. So trying to detect a specific delicate memory trace, like the concept of an apple, during deep sleep, it's sort of like trying to hear someone whisper the word apple while you are standing next to the speakers at a heavy metal concert?
That is, yeah, the heavy metal concert analogy captures the exact problem. Those slow oscillations are the heavy metal music. They're deafeningly loud on the electrical readout.
Right.
And the whisper is the subtle reactivation of the memory. And we know that this tiny reactivation is crucial for memory consolidation.
Consolidation meaning moving the short-term memory to long-term.
Exactly. The biological process of the brain moving short-term memories into permanent storage.
But wait, if I'm like an audio engineer and I have a loud rhythmic bassline noise polluting my track, I just filter it out.
Right. You'd apply a high-pass filter or something.
Exactly. I isolate the frequency of the whisper and I digitally delete the heavy metal track. Why can't the researchers just apply a filter to remove the slow oscillations from the data?
Because in a standard audio file, the noise and the vocal track are separate entities, right?
Yeah.
But in the brain, the whisper and the heavy metal concert are physically and biologically entangled.
Entangled how?
The subtle memory reactivation relies on the energy of those massive rhythms to actually happen. You cannot surgically delete the slow oscillation without completely obliterating the fragile signal of the memory itself.
Oh, wow.
Yeah. If you strip away the heavy metal wave, you destroy the very memory trace you were trying to read.
Wow. So traditional filtering just completely fails because the signal is inextricably bound to the noise. Let's do a quick recap here to lock this in for you listening. Your brain locks its daily memories inside these massive electrical waves during sleep to process them.
Yep.
And previous AI models, which were only trained on the clear, quiet signals of awake brains, just got deafened by the loud waves of sleep.
Which forced the researchers to build an entirely new type of model architecture. They called it the sleep interpreter, or SI.
And SI is pronounced Si in Chinese, right? Which means thinking.
Yes, beautifully translates to thinking. Now, to train this model, they couldn't just use standard waking data. They had to create an ingenious framework called the Targeted Semantic Reactivation, or TSR dataset.
I love how they set this up. So to give you a mental image, they took these 135 participants and trained them while they were wide awake using 15 specific semantic categories.
Right.
For example, they would show the participant a picture of a sheep and simultaneously play the ba sound of a sheep. They drilled this in so the participants heavily associated the core concept of a sheep with that specific sound.
Creating a really strong neural link.
Exactly. Then they put the participants to bed, and while they were deeply asleep, the researchers gently played those exact same sounds back to them.
And that setup gave the researchers a critical timeline, because they knew the exact millisecond the sleeping brain was being prompted to think about a sheep.
Because they just played the sound.
Right. But knowing when the thought occurs doesn't solve the translation problem of actually reading the thought through that heavy metal noise.
True.
To solve that, they employed a highly advanced AI mechanism called neural contrastive learning. The sleep interpreter uses 3 separate encoders: a wake image encoder, a wake audio encoder, and a sleep audio encoder.
Okay, let's break down what is actually happening inside these encoders, because this gets into the AI weeds a bit. They are combining 2 heavy-hitting AI architectures: convolutional modules and transformer module.
A really powerful combo.
Right. So a convolutional module, or CNN, is fantastic at spotting immediate split-second local patterns in the raw brainwaves.
Yep.
It's kind of like looking at a single frame of a movie and instantly identifying a character. But the transformer module, which, by the way, is the same tech behind large language models like the ones we use every day, it captures global synchronization.
Exactly. It understands the wider context of what the entire brain is doing over time. So it doesn't just see the single frame. It understands the whole plot of the movie.
Right.
And when you combine them, the encoders translate the raw, chaotic brainwaves into a high-dimensional mathematical language. But the true genius here lies in the contrastive loss function.
Okay, explain that. What is a contrastive loss function?
Think of this as a rigorous spatial map that the AI is forced to build. The mathematical rule of contrastive learning dictates that the AI is heavily penalized if it places the neural representation of the awake brain seeing a sheep far away from the sleeping brain hearing a sheep.
Oh, so instead of acting like a simple dictionary, it's like the AI is acting as a master cryptographer.
Exactly.
It doesn't matter if the message is written in the frantic, high-frequency shorthand of the waking mind or the slow, sprawling calligraphy of deep sleep.
The AI is forced to pull the sheep awake and sheep-sleeping brainwave patterns incredibly close together in a shared mathematical space.
While pushing different concepts away.
Yes. At the exact same time, it is mathematically forced to push the representation of a sheep and the representation of a book as far apart as possible.
That is so clever.
It really is. By organizing the data through semantic meaning rather than raw electrical similarity, the AI learns to naturally bypass the background noise of the sleep stages.
It decodes the heavy metal without destroying the whisper.
Exactly, because it has mapped exactly what the core concept of the whisper looks like across completely different physiological domains.
Okay, let's pause for another quick recap for you listening. So the researchers solved the generalization gap not by filtering the brainwaves, but by forcing an AI to map the deeper meaning of concepts into a shared space.
Right.
Completely ignoring whether the brain was awake or asleep. Now, once they had this master cryptographer that could decipher the sleep state, the researchers turned it toward one of the most stubborn mysteries in neuroscience.
Timing.
Timing. When exactly does the sleeping brain choose to replay our memories?
And the decoding accuracy of the AI revealed that memory consolidation isn't just, a flat, continuous process across the whole night. The brain utilizes a highly specific golden window for processing these semantic memories.
A golden window.
Yeah. To find this window, the researchers took that massive, slow brainwave, the slow oscillation, and divided its life cycle into 8 distinct phases.
Right, so picture a massive ocean wave. The trough, or the very bottom of the wave, is the down phase. Then you have the climb upwards, the peak at the top, and the crash back down.
Precisely.
So they tracked everything, the pre-SO, the transition to the first up peak, the transition down, and so on. And they zeroed in on one absolute critical fraction of a second, the transition to the first up state.
Yes.
This is the exact moment the brainwave is aggressively climbing out of the deep trough and accelerating toward its peak.
But the true biological magic happens when that upward climbing phase perfectly couples with another distinct brain pattern called a sleep spindle.
What's a sleep spindle?
A sleep spindle is a very quick, high-frequency burst of brain activity. It vibrates around 12 to 16 hertz.
Okay.
When the auditory cue lands right at that transition climbing phase and a high-frequency sleep spindle fires at the exact same moment, the sleep interpreter's decoding accuracy skyrocketed to 40.02%.
Let me just pause to emphasize the magnitude of that number for you listening. A 40.02% accuracy rate in a test with 15 completely different semantic categories.
That's huge.
Random chance is only 6.7%. So the AI was reading the brain's thoughts with astonishing clarity. So, what does this actually mean biologically? Memory isn't just constantly playing on a loop all night long.
Not at all.
The brain is literally waiting for the exact crest of this slow brainwave, pairing it with a high-frequency spindle burst to hit save on what we learned that day.
It perfectly validates our broader theories of systems consolidation. You see, the hippocampus is the brain's short-term memory center. It temporarily holds our daily experiences.
Like RAM in a computer.
Great analogy, yeah. But for long-term, permanent storage, those memories have to be physically transferred to the neocortex. This research provides hard evidence that this transfer doesn't just seep over randomly.
Right.
It happens in highly coordinated, explosive bursts, specifically during these SO spindle coupling events. That exact millisecond is when the brain's upload cable is plugged in and transmitting data.
Okay, that is just mind-blowing biology. But I have to play the skeptic here, and I'm sure you listening might be wondering the exact same thing. I'm struggling to buy this whole premise a little bit.
Okay, hit me.
If you were blasting a boss sound into a person's ear while they sleep, of course their auditory cortex is going to light up. Aren't we just building an AI that detects the brain reacting to a physical noise rather than the brain actually thinking about the abstract concept of a sheep?
Oh, that's the primary critique, right.
Yeah.
And the researchers anticipated that exact argument. To prove the system wasn't just catching an acoustic echo, they designed 2 rigorous out-of-sample validation experiments.
How did they set that up?
Well, in validation experiment 1, they brought in 22 entirely new people who had never been trained on the sheep sounds. They used a classic targeted memory reactivation, or TMR, setup, but they fundamentally changed the rules.
Okay.
They did not use the original 15 concepts, and crucially, they did not use semantic sounds.
Right, they used completely arbitrary sounds.
Exactly.
So during the waking phase, they would show the new participant a picture of an apple, but they would play a completely random, non-semantic electronic beep.
Yeah, just a tone.
There is nothing about a beep that inherently means apple. To make it even harder, they had the participants learn 120 different verbs associated with these concepts. So you see an apple, hear a beep, and memorize the verb throw.
Then the participants took a nap. During the nap, the researchers played those arbitrary beeps at specific slow oscillation phases. They took the sleep interpreter model straight off the shelf without retraining it on any of these new arbitrary sounds and applied it to the live EEG data.
And it successfully decoded the concepts.
It did.
When the random beep played, the AI read the brainwaves and output apple. I mean, it proved beyond a doubt that the AI wasn't just hearing a ba sound. It was reading the abstract, internal concept of the item that the tone triggered.
And the results went even deeper than mere detection. The decoding probability directly correlated with actual post-nap memory improvement.
Wait, really? So it predicted how well they'd remember?
Exactly. The correlation coefficients were statistically solid, ranging between an R of 0.534 and 0.588.
Okay, what does that mean practically?
Practically speaking, this means the stronger the AI could decode the memory replay during that sleep spindle window, the better the participant remembered the specific verbs when they woke up.
That is incredible. But as I was reading the paper, I kept looking for the ultimate proof.
The spontaneous test.
Yes. What if there is no external sound at all? I mean, think about it. We dream and consolidate memories every single night without scientists playing beeps into our ears. what happens in a completely silent room?
That requirement birthed Validation Experiment 2. They brought in 25 new participants for a study focused entirely on spontaneous reactivation. Each person completed 2 separate sessions, spaced a full week apart.
Right.
One session focused entirely on learning deep associations with the concept of an apple, and the other focused purely on a book.
So they learned 40 different verb associations for each concept, took a baseline memory test, and then went to sleep. Total silence. No cueing, no beeps, no sounds. Just a person sleeping naturally.
Yes, and during this completely soundless sleep, the researchers told the AI to look exclusively at those golden windows, the moments of spindle coupling.
The upload moments.
Exactly. Once again, the off-the-shelf AI successfully detected spontaneous Apple memory replays after the Apple session and spontaneous book replays after the book session.
With no prompts.
None. And just like the first experiment, the mathematical strength of the spontaneous decoding tracked directly with the participants' memory retention, showing a correlation of 0.483.
So let's do another quick subtopic recap here, because this is the absolute crux of why you should care about this study. These 2 validation experiments prove that this AI is reading endogenous internal thoughts.
Yeah.
It is literally watching the brain spontaneously open its own internal filing cabinet and review the day's files, entirely unprompted by the outside world.
It's revolutionary.
Well-
But, validating that the AI can read these memories after the fact is great for a highly controlled lab setting. Analyzing terabytes of data days after a sleep study doesn't help us actively interact with the brain.
Right.
To translate this into a viable medical or performance tool, you need to catch the brain in the act.
Which brings us to the real-time system, moving from retroactive data analysis to a live dashboard of the human mind. So to do this live, you have to know exactly what stage of sleep the person is in instantly.
And usually sleep staging is painstakingly done offline by human experts looking at pages of squiggly lines. So the team had to build a completely automated module called SI staging.
How does that work?
The architecture of SI staging is incredibly lean and efficient. They paired a convolutional neural network with a long short-term memory network, or LSTM.
Okay, so the CNN identifies the immediate micropatterns in the waves, right?
Yeah.
While the LSTM retains a memory of the prior waves to track how the sleep architecture is evolving over time. And they run this using just 3 data channels.
Right, which is wild. Just 3.
They use a single EEG sensor on the scalp known as C3, an EOG sensor, and an EMG. Let me just explain those details really quick for you listening. C3 is just measuring the brain waves on the top of the head. EOG tracks eye movement, right?
Yes, to detect rapid eye movement or REM sleep.
And EMG tracks muscle activity, because your muscles literally paralyze during certain stages of sleep. So just those 3 channels. And yet it matches human expert accuracy at 90.38%.
But the latency is what makes this a real-time system. Depending on the computer hardware, it processes the sleep stage in roughly 300 to 432 milliseconds.
Less than half a second.
Exactly. Once this SI staging module detects that the participant has been in a stable deep sleep state for 30 seconds, it acts as the master switch. It essentially says, okay, we are locked into deep sleep, deploy the mind reader.
That master switch triggers the main SIMD decoder. The decoder then begins ingesting the live whole brain EEG data and outputs the semantic label of what the brain is processing right in that very moment.
Yeah.
And there is a detail hidden in the methodology of the paper that is just incredibly fun. To make this data intuitive for a human to watch, they took that live decoded semantic label, say, the AI outputs the word sheep, and piped it directly into a text-to-image AI model called Stable Diffusion V15.
I love this part.
So picture this in your mind. You are the researcher sitting at a desk in a dimly lit lab. Your subject is fast asleep in the next room, and you are literally watching a computer monitor generate visual images of sheep or apples or books in real time as the sleeping person processes them.
It's like watching a movie of their thoughts.
It is a live visual broadcast of memory consolidation.
And the implications of a real-time system with sub-second latency stretch far beyond visual novelty. It allows for closed-loop interventions.
Closed loop meaning the system reacts automatically.
Exactly. We now have the technological capability to deliver a targeted therapeutic cue, whether that is a specific sound or a gentle, non-invasive electrical stimulation at the exact millisecond. The brain enters that golden transition to first up window.
Think about what that means for human performance. Have you ever wondered what you could learn in your sleep? You could theoretically enhance learning for a medical student studying for board exams, delivering subperceptual cues that accelerate how fast their brain physically wires that information into long-term storage.
Or, moving to the clinical side, you could deliver therapies to treat severe memory-related disorders.
Right.
We could potentially dampen traumatic memories in PTSD patients by precisely intervening while the brain is actively processing that specific trauma during the night.
We are crossing a major threshold here. We are moving from passively observing sleep as a mysterious biological necessity to having a direct two-way dialogue with the sleeping brain,
Utilizing its own natural mechanisms to optimize cognitive health.
So let's take a breath and recap this incredible journey from start to finish. We started with the noisy, chaotic electrical signals of the sleeping brain, the generalization gap that acted like a heavy metal concert hiding a crucial whisper.
Right.
We saw how the elegant math of neural contrastive learning built a master cryptographer, mapping our concepts into a shared mathematical space regardless of whether we are awake or asleep.
Brilliant engineering.
Then we pinpointed the exact fraction of a second, the SO spindle coupling, when the biological upload cable is plugged in and memories are saved to the hard drive.
Yep.
And finally, we saw all of this technology combined into a live, real-time dashboard of human thoughts.
It serves as a remarkable demonstration of how large data sets and highly advanced AI architectures can extract profound biological truths from signals we previously dismissed as far too noisy to interpret.
It really is a triumph of neuroscience and engineering, and it leaves me with this final thought for you to ponder. At the beginning of this deep dive, we talked about the sleeping mind as a locked vault. Well, the door is wide open now.
Wide open.
If we now have a tool that can decode your thoughts and a system that can target specific memories exactly when they're being consolidated, how long until sleep therapy means actively curating your brain's nightly playlist? If you could choose to drastically strengthen a specific skill you learned that day or quietly erase a specific crippling fear while you sleep tonight, would you let an AI DJ your dreams?
The timeline for that kind of intervention is approaching much faster than we think.
It really is. Thank you for joining us on this deep dive into the sleep interpreter. Keep questioning the world around you, and we'll see you next time.